What did you change?
Now I still opening. What I will change is okay. I open so desktop. So okay. So since we saw that it works, I will do here. I'll change again this one, then I save because it works. Put everything. Okay, then this we said that was big. Here we put 200. So we increase the CO2 is constant at 3. And now we increase the water and we investigate 2% of these conditions. I will say I normalize. Okay. And then I run.
No,
Pero ahorita no encuentro dónde
si no lo tienes en domingo, y le dice dónde. Because you don't save the nets out first.
Yeah.
Then it just overwrites, right?
Yes.
Okay, well,
Yes.
Next time. No, esto estaba bien.
era 200. Sì,
3 diviso 2.
3, yeah.
Yo ya guardaba.
Ah, pues
Lo guardé.
antes de normalizar.
Sí, ahora sí. Antes no lo veo.
Bueno, antes de normalizar.
Lo guardé.
Ah, ok.
Entonces ya lo tengo.
Ajá, pues ya-
Y ahorita lo cambié pues, el agua. Sí,
Es que no les pasa que no pueden cambiar de repente siempre los valores. ¿Sí?
Sí.
Por ejemplo, ahora que lo modifican los CO2 y los.
Claro, eso, ¿no? Sí. Fabio, sorry. You change the fugacity?
No,
No?
no,
No. Los normales, ¿no?
¿No lo haces?
Sí.
Muy bien, muy bien.
Ahora tienes que ver un
Pues,
día.
aquí están los valores de la tabla. Si quieres empezar. Pero cuando es 0.35, el valor es 25.
No, 20. Porque no cambió la temperatura.
¿Qué pasó? ¿Ves? Por eso lo puso mal. Y por eso tengo ahorita no sé de esas cosas, no sé nada.
Que no puedo cambiar el CO2. Puede cambiar el valor del agua, pero no del CO2. No me deje cambiar.
Cancelar no tampoco.
No,
Si no abres todo de nuevo.
ahí ahora sí.
203.
Ajá.
yes.
Y el primero era 100.
100, no, 3. We are fixing 3. Okay, because what we need to understand, so what the philosophy is, we have to understand if the number that we are putting there, particularly the CO2, is undersaturated or saturated. So what we see that since we increase the water, the results of the CO2 here is still 0.03. So it means that we are using values that are below the saturation. So basically, if we increase the water, we not change the solubility of CO2 in this melt because we are too low in CO2. I think the next step, we have to increase the CO2. So basically what we are doing is this. So we have this diagram, we are simulating 200 megapascal, okay? And we fixed, like in this case, we fixed like 1000 ppm, no? We are changing the water, but with 1000 ppm, we are still always below the saturation. So the value for 200 megapascal of the CO2 is much higher than 1000. So what we are experiencing here is this. We selected the number, so basically 3000 ppm, that is not enough for this basalt. Okay? We have to increase the amount of CO2 to reach the saturation, because changing the water, nothing happens. You see what it means? Okay. So therefore, the next step, what we need to do is we try to put like 0.08, just an exaggeration of CO2, and we rerun with 2% of water. And what we should see that we should have basically, also if you see here, the simulation give you the liquid without any fluids. So it means that not having fluids as a phase, it means all the fluids that we put are dissolved into the liquid, but we are still we have not reached the saturation of water and CO2. And for water, we know that we didn't reach the saturation. The point is that because at 200 megapascal, more or less, the solubility of water should be, just to make clear what the philosophy is this one. So if we go for the this one. This is the solubility of basalts. Here is no. So 200 megapascal anyway will be around 3.5 4. No, so 2% of water, we know that we are below the saturation, so that's fine. The point is that we have to understand what the saturation of CO2 is to draw this diagram here. So, and because the point is that this curve will go to 0 for CO2 when we reach the maximum saturation of water for that pressure. So when just water will dominate as a fluid into the system. So basically, in this basalt, that is a more evolved basalt than what we are simulating, at 50 megapascal, so at 2.2, more or less, here is just water saturated there. And then if we decrease the amount of water, will increase basically the amount of CO2 that can be dissolved into the system. And there is, of course, there is a partition coefficient between the two in the. So what we are trying to do is to understand the maximum amount of CO2 that can enter in this. So therefore, what we need to do is just to close it, throw away everything, and restart. What is it? Environment. Yes. Then this point, instead of 3, I put something really incredible, 9, something. So I put 9 for CO2, just to make something extremely high.
So this starting conditions in CO2. Which numbers?
2, 9.
No, no puede ser. No borré. No, soy una.
No, no, a ver,
0.001. And
no, no soy la
no, this is percentage. No. By a factor of 10,000. So 10,000. Yeah, so 3 weight percent would be 30,000. 1 weight percent is 10,000. Yeah. Yeah. I mean, one weight percent.
0.1. Y 9.
1 weight percent is 10,000. Yeah, so 0.01 is 1,000. Yeah.
0.01 1,000.
Yeah, no, 100.
Ahora sí hay.
100 ppm is 0.01 weight percent.
Sí,
1,000 ppm is 0.1.
Okay, so before we put wrong for that reason, it's unsaturated because we put the wrong number. Oh, okay, okay.
So, but CO2, where is the, is in the liquid or where?
This is just in the liquid.
Okay,
This is just in the liquid, but I understood that we did the calculation. So from ppm to weight percent is no 0.0,
0.0.
but 0.3.
0.3.
0.3.
Yeah.
Right. Okay. For that reason, that doesn't work. So basically, it's okay. So we tested all the undersaturated conditions. So what we need to do is,
Well, to do it again with the.
yeah, with the right values that yes, yes, yeah, command. Oh, so therefore it's it should be to 30. It should be 30.
We change 200 and
30 should be, yeah. Okay, now it works. Yes. Okay. That makes sense. So now we have the fluid as a result of phase because we put too much CO2 and too much CO2. So therefore, as a fluid, basically, here you have the proportion of water and CO2 released into the fluids. Basically, the fluids represent bubbles here. So the exhaled gas from the liquid. And we have mostly 70% CO2 and 30% water, basically exhaled in this system. And the solubility is 1.92 weight percent H2O, okay, and 1,100 ppm of CO2. That makes sense. So therefore,
Sorry, how much original values water?
The original value of water we put around 1.200, yes. Then we have to you normalize and it will be more or less this number. And then the calculation will say, okay, this is in equilibrium, this is out. Okay. So in equilibrium is 1.92, and as ppm is 1,100. Okay, so therefore we have to repeat that one at 1 weight% of water, okay, because of course it was wrong. So therefore we close and we repeat.
So in both experiments, water is at 200,
In this one, yes, now that we change to 100, keeping the CO2 always at 30. Okay, we fix the CO2, we change the water.
So first we fix the water, we change the CO2, now we're fixing CO2.
So no,
The first one was
Okay, so the first one we have to do what was it?
so now we have to repeat this because when we put the CO2, we put 3 instead of 30. So we have to fix the CO2 at 3000 ppm. That it means 0.3 weight% of water. Okay. So now it's just we open the system, we open this one. Open next. So basically what we need to do is always keep this at 30. Okay. If the CO2 is fixed, what we are investigating is the amount of CO2. So instead 200, we put 100. Okay. We keep everything as before in terms of intensive variable. Okay, normalize. And then I execute again. Here. Okay, and now we have 0.98 as a solubility of water at 100 megapascal. So basically at 200 megapascal, so it's close to 1 weight% of water. With this water, the amount of CO2 is basically 1,200 ppm. So basically in our Excel file, we put 0.98, okay, and 1,200, okay. So what we want to do now is we want to reach 3 weight% of water and see with 3 weight% of water where the CO2, how much CO2 will be dissolved. So basically we expect it will be lower than 1100. Okay, so based on this cube, we are going like this: a low water content, higher CO2, and we are decreasing this way. Okay. So therefore we close again our simulation. So, And again. Yes. Oh, yes. Comments. Okay, now I go to 300, so we want to be closer to 3%. And normalize. And execute out. And check the results. Okay. We go at 2.81 as a solubility of water, 0.09. So we go to 900 ppm. So 2.81, 2.81, 900 ppm. Okay. This philosophy we can repeat for 100 megapascal, exactly the same. So 100 megapascal. Or we want to investigate again 1 weight% of water, 2 weight% of water, 3 weight% of water, and we see the amount of CO2 dissolved with that amount of water at 100 megapascal. So therefore we do it. We have to just repeat because Maths doesn't like to run multiple simulation on the same. If you want to do multiple simulation with Maths, you have to just adapt the script with like MATLAB or something like this, where you run Maths continuously, something like this. In order to avoid to reopen everything. It's boring, but at the moment everything will do different. Okay. Again. That's not yes. The command open desktop. Okay. Now, tensor variable we change to 1000 bar. 1000 bar. Say okay. We say okay. We have already. We start from nearly 1 weight%, and we do normalize. Execute out. 100. Yes, we start from 1 weight%. Yes. Okay. Now we have, as a solubility, we have 0.97 and 600 ppm. 197 0.97, 600 ppm. Yeah. Yeah. As you can see, the amount of CO2 dissolved at 100 megapascal is more or less half of the 2000 megapascal. So therefore, what we are doing is 100 megapascal will be like here, okay, at the 1% of water. Is not so far from this. This also is a kind of basalt. So it means that if you're at the end, when we plot our cubes, if your met inclusion will be with this amount of CO2, you know that you are closer to 100 megapascal than 200 megapascal. You are constrained in some way the pre-reactive or synreactive conditions. So therefore, we repeat at 2 weight% of water, and then 3 weight% of water, and then we plot the cubes. Before we change the water up to 100. Is always 100. 100 megapascals and 1000. The result is 185, 400. $1.85, 400. Okay. And then we do the last step is with 3 weight% of water, and we see what we get. With 3 weight% of water. And the same pressure, same temperature, everything the same. Okay. The last time. Yes. Okay. Okay. And we get that here the solubility of water is 2.53 and CO2 is 200. 2.53, 2.52, 200. Okay. Now what we can do is just to plot them in the diagram. Like this carpet diagram. This. Okay. What we can do is to add that data. I can have the series. Let's do X is let's go. Oops, in CO2. Okay. And this is still 100. So basically, this is the curve of 200 megapascal. This is 100. This is CO2 in ppm. This is water with percent. So we reproduce the curves that I showed you before. At that point, you can do as much as you can in simulation. You can do up to 50, 20 megapascal as you like. You can investigate the range of pressure that you want. You will have this curve with the solubility of water and CO2. And then what you need to do is just to plot your data. So you have to measure your melting inclusion or whatever, your water and CO2 and plot that and see and where does it go. Because if we cluster here, means that your reactive condition of 100 megapascal, if it's higher, it means that, or if it's in between 200 and 100, it will be something that you can investigate with maths. You can do 100.
For example, I could use my initial composition from the melts, basaltic melt, that I did melt in the microscope.
Yeah.
I plotted and I simulated water and CO2 with that melt composition,
Yes.
and then I analyze water inclusion.
Yeah.
And plotted in that model.
Right? Yeah, you need water and CO2. Because at the end there are two variables there, and just water will not fix you. You have to fix also the amount of CO2 dissolved. So therefore, what we did here in this diagram, for instance, was we measured water and CO2. The water was measured with Raman and with SIMS, and the CO2 just with SIMS, for instance, for our melting inclusion. And just this is the Masaya volcanic system in Nicaragua. And you see the Fontana Lapilli pinion eruption goes from here to here. You can follow a decompression part of the system, for instance. If you see the Masaya triple layer, instead it was just clustered between 50 and 100 megapascal. So it means that probably the productive condition of Masaya triple layer were possibly the maximum was around 50 megapascal. So this is what I mean. So you can do that, and you can constrain your productive condition based on water and CO2 solubility.
No, but the first composition was what came from the data, the CO.
Ah, the CO2.
No, the chemical data.
At the beginning, I just took a basalt.
Okay.
It's a random. No, I just put a basalt, a random basalt. So just I collected, I prepared this file.
No, but in a real case.
In the real case, I don't know. This I took from a book. Just
take a reference.
Yeah, I took just a basalt just in the simulation.
Even for your diagram.
For my diagram here, this is we used basically Masaya triple layer and Fontana Lapilli. The two lines here represent two bulk compositions.
Okay.
One for Fontana Lapilli and the other one for triple layer.
Okay.
So both of them are highly explosive eruption from Masaya volcanic system in Nicaragua. But since one is a pure basalt and the other one is the basaltic andesite, we calculate So the solubility for both of them, because
Okay.
one is just more about
One question, would you prefer using the melt composition for microscope, or can you use a whole rock?
You can use also the wall rock. It's the answer for your starting point is the wall rock.
Okay.
Is the wall rock. So so therefore you have two options to do the wall rock. Or you take your scoria or lava and you remelt everything, and you measure the glass in the microscope,
Yeah,
or you make the powder as I show you.
my question is because, for example, when you got like magma, you see your sample has two different melts, basalt and rhyolite. Would you do it for the two of them?
Yeah, I think so.
But and then you need the microscope.
Yeah. I think so.
Whole
Because
rock,
if you do the wall rock, it doesn't
Yeah, whole
represent the whole.
so whole rock only if you think it's representative.
So, yeah, if you have a mixed stuff, the risk is that if you do the bulk, you will not represent either.
But then you can also more or less constrain the pressure at which both might have encounter mix if you do them separately.
Yeah, I think so. I think so. If you do carefully the analysis in detail.
I mean, and you get CO2 and water from each one separately.
Yeah, you can do it. I think so. Yeah. So at the point you would see where. Yeah, and then you can constrain these kind of things with the phase diagram we will do tomorrow in order to understand if then this magma at those conditions can crystallize, is very close to the liquidus, is above the liquidus, or it's far away below the solidus, so therefore it's not realistic that mixing will be occur, for instance. So you can have a range of conditions where you can be really close to the liquidus and far away. So, and this will give you information about, for instance, if mixing is possible, or just instead you expect mingling instead of mixing, because chemical diffusion will be inhibited in some way, because crystallization will dominate the system. So this kind of you have to put everything together. This can be just a starting point to constrain.
Very powerful.
Yeah, the Kela Jacobino, the paper that I showed you before, they made basically this vesicle that, but I have not shown today because you need to know, you have to install Python and another program that is Anaconda, and you have to know how to write in Python in order to launch the condition. So I thought that maths was much easier to do. So, and it's quite reliable. If you want to have the more updated model, is the Kela Jacobino one. But as I told you, you have to know how to run. So there you have basically all the models in one system, and it will choose the best for you. Yeah, the best of transaction. But still, I found this very powerful to use, and at least you will have, as a first estimation for sure, you can say where you are. I don't think the results of this will be far away from, because this program, MagmaSat, is in Vesica, so therefore it's not going to be so far.
So basically, this eruption of Masaya fragmentation must have happened around 50 megapascals.
50, so basically what we saw is that the Masaya triple layer was stored more or less between 70 and 50 megapascal. The storage was quite more shallower than the Fontana Lapilli. Fontana Lapilli, instead, we see a quite nice trend of decompression.
Yeah, it was like decompressed straight to the
yeah, and it's also Fontana Lapilli has much more layers. It's like several, if I remember correctly, 7 pools of linear eruptions in several months. Probably the storage probably moved a little bit during this. Instead of triple layers, there are just 3 pools of the eruption.
And when you have a pathway this, can you use like the pressures to constrain like something like ascension rates of the magma?
The ascent, yes, in theory, yes. If you have a nice trend like that, you can say something about the yeah.
And have you compared like how the MELS model correlates, for example, with the ascent rates and calculations from the vesicles, crystal number densities? Have you constrained the two methods?
What do you mean exactly?
Like if you get data, for example, of ascent rate or the compression rates
Yeah.
from the vesicle number density or the crystal number density,
So
how they compare?
this we did with mostly we did with Giuseppe's model, that is the MAMMA model. I'll present what I presented today in this diagram, basically. It's the last slides that I presented. This is a conduit model that was developed by Giuseppe Laspina. What is this in front of it? I don't understand. Anyway, where this model considers the different ascent rates. Of course, the ascent rates is an output of the model, is not an input. But what you can get, what you can associate is the compression rate and ascent rates with the not with the vesicle number density, but the vesicle fraction and crystal fraction. These kind of models are not still able to track the crystal number density or vesicle number density, but they can say if the connectivity is developed or not, and when. If the bubbles and melt are coupled together. So if there is connectivity, but still is not enough because the ascent rate is too fast, so the four bubble will not escape, so gas will not escape. Can tell you about vesicle fraction and crystal fraction, but no vesicle number density yet. It's something that can be developed, but not ready yet to do it.
And considering the same shape, they all start.
This is a good question. No, the model considers the evolution of the shapes. Yes.
Okay.
So in terms of capillary number, what I showed you before, if the people of the bubble are elongated or spherical, yes, this model will tell you if this, because it's in the rheological model. The rheological model here is quite advanced. It's considering disequilibrium and crystallization and vesiculation. That I'll explain better what it means. And it considers the crystal shape and vesicle shape in the rheological model. Yes. So basically, just to be clear, my stuff sometimes disappear. This okay. Just to answer your question, here is the paper of Giuseppe, and what we did for Etna and Kilauea, we investigated just show Etna. So we investigated different kind of conditions. These are more than 10,000 simulations with this model. And you see the output is that you have decompression rate that in some way is associated with the ascent rate, and varying the variables, which solution are effusive, the blue one, which are highly explosive, like plinium, the red one, and the green and yellow one are the lava fountain. So therefore, with the very fast ascent rates and the compression rates, you go towards fountaining, and then if you are in the middle, basically it's a highly split opinion. If you are too slow, basically you have the crystallization will advance to it's too much, and then basically logically so gas will decouple, and you have the gas magma. Basically, that's it. You have to cross all the variables to understand this, but it's what you can get. Of course, this an advanced model. But melts at least give you a picture of the equilibrium.
Yeah.
So
No, it's a power of the different dynamics with synchrotron data with the residual.
yeah, absolutely. So that you have in that information you have the crystal fraction. I will show tomorrow the simulation in order to reproduce a phase diagram at the equilibrium condition with equilibrium crystallization. We see also how the crystal fraction can vary as a function of temperature and pressure, and you have also information about the chemistry of the minerals. You can basically compare the condition that you put in melts with the anorthite content in the plagioclase, for instance, or the composition of pyroxene, or the olivine, the fosterite composition in olivine, and compare with your natural sample in order to say, okay, I match this anorthite number with these conditions. So that is possible to do. It's more reliable with basalts or basaltic andesite. We have tested with dacite. At the moment, we are working on dacites. There is some, we compared with our equilibrium experiments, maybe. There is a gap. The pyroxene is quite precise. The plagioclase can vary 20, 30 dB. There is an error of 20, 30 dB, but I think with melts is acceptable for more evolved magma. With basalt or basaltic andesite or andesite is quite precise.
So in your experiment, you can control oxygen.
Yes, in experiments you can control oxygen. I'll show that. Yes.
En línea sobrevivieron Daniel y Plan. Daniel, ¿todo bien? ¿Lo lograste?
Sí, pude instalarlo ya.
Se escucha el pero, a ver, abre tu audio.
My audio is open.
Daniel.
Hi. Do you listen me?
Daniel, ¿no se escuchas?
Sí.
No, yo no. A ver, ahorita.
¿Sí? ¿Me escuchan?
Sí, ahorita sí.
Okay. Yes, I can install the melts in Ubuntu. And I'm trying the examples, but in the melts archive don't appears nothing.
A ver, guardé la presentación, digo, el video, ahorita lo grabamos.
Okay.
Te puedo compartir la liga, porque al principio no salían los datos porque estaba mal el input adentro del archivo.
Ok. Entonces checo el video para mañana.
Checa el video y mañana cualquier cosa lo volvemos a replicar.
Sí, está bien.
¿Listo?
Muchas
¿Dónde
gracias.
estás tú?
¿Cómo, perdón?
¿Tú dónde estás? ¿Aquí en Ciudad de México?
En Morelia.
Ah, en Morelia, va. Ok, listo. Va, chécalo y cualquier cosa mañana lo revisamos.
Ok, sí, muchas gracias.
¿Sí? Listo. Va. Citlali, tu tesis, exacto.
Sí, profesora, exactamente.
No, así. ¿Para cuándo?
Ya pronto, próximamente, doctora.
No, ya.
Sí, sí, ya me estoy
Ponte,
apurando,
ponete
doctora.
atrás de aquí. Edward, pues junta a los dos en un cuartito negro. Nos salen hasta que tengan algo. ¿Dónde estás tú
Sí,
ahorita?
sí.
¿En Ciudad de México?
Sí, así es, doctora.
Muy bien. Listo, por hoy.
Yeah.
Per oggi è fatta, no?
Yes, yes.
Nos vemos mañana.
Hasta
Nos
mañana.
vemos, gracias.
He works.